Hello everybody, welcome back. Today we're going to be talking about Clue 4, which is Fieldwork in Japan. We will be doing this lesson in two parts, so we're starting the first part and we'll do the second part another night. For today's lesson, you are going to need your notebook, so make sure you have that out and ready to go before we begin. The first thing you're going to want to do is start a new page for Clue 4 vocabulary. You're going to want to add these words to it, leave space in between all of them for you to write the definitions. Pause the video now so that you can do that. And in this clue, we're going to be examining a few things. First of all, our goal is going to be to look at, are all volcanoes the same? And I'll give you a hint, they are not. What types of lava flows, what types of eruptions are there? And we're going to try to understand what types of volcanoes or landforms we see at different boundaries, because we will see different ones forming depending on the type of boundary. So before I get going on the clue, I wanted to review a couple of important things from our previous clue, Clue 3. And first of all, we want to remind ourselves viscosity is the resistance to flow. So high honey, if something resists flow like honey, it's got high viscosity. If it flows easily like water, it's got low viscosity. And magma's viscosity can vary depending on what its temperature is and what silica content is. And remember, silica is that compound that makes it hard for magma to flow. Right, so a high silica content in the magma means a high viscosity, kind of thick, sticky magma. And the higher the temperature of the magma, the lower the viscosity. So remember, higher temperature makes things runnier. Think of putting syrup or honey in the microwave. And then the other thing I wanted to remind us of is where volcanoes can actually be formed. And one of those places is at a divergent boundary, like the one at the mid-Atlantic ridge and at Iceland. You'll see two plates moving apart, and that hot molten magma from below is able to force its way to the top and replace that space. So you end up creating new land at a divergent boundary, and you get volcanoes, like the one along the mid-Atlantic ridge, that long mountain range of volcanoes underwater. You also get volcanoes forming at hot spots. Hot spots don't have to occur at a plate boundary. They can occur right in the middle of a plate, like in Hawaii, in the middle of the Pacific. And it's just a weak spot in the crust where magma was able to force its way up. So very similar to a divergent boundary, you get a volcano that's just hot magma coming up from below at a weak location. The other way that you get volcanoes is a little bit different. You can get volcanoes at subduction zones, at convergent boundaries. So you'll see volcanoes forming where one plate is subducting underneath another. And this is kind of a recycling of rock. You get this recycling process where the rock is being forced underneath, it heats up and melts, turned back into magma that then rises and creates a new volcano. And the process kind of starts over. So it's a little bit of a recycling process. You get different types of magma because of this, as we'll see. So the question I want to pose to you is, how are Japan's volcanoes different from the volcanoes you might see in Iceland or Hawaii? Remember, Iceland is a divergent boundary. Hawaii is a hot spot. So at both those locations, it's just molten magma coming up from underneath at weak locations in the Earth's crust. Japan's a little bit different, so we're going to see the difference in the lava that comes out at those locations. We'll start with Iceland. This is the Bardarbunga volcano in Iceland, and it's at a divergent boundary. You can see it looks like kind of just a big gash in the earth. It doesn't look like the typical volcano you'd think of because it is a divergent boundary. Right? Magma's coming up to the surface. And look at this lava. It's low viscosity. It's flowing almost like water, very easily. All right, so let's compare that to what we'd see in Hawaii at a hot spot. All right, and we can see here that it's a little bit slower than the Iceland. It's not quite as low viscosity, but it's still pretty low flowing low viscosity lava. Some nice pahoehoe. Right, so let's now look at the Japan volcano. This is Sakurajima in Japan, and already we see it's very different. We can't really see any magma pouring out of it, any lava pouring out of it. We do see a big explosion. We see a lot of ash and cinder and soot being thrown into the air. This is a very different type of eruption, a very different type of volcano. So what is it about Japan that makes it different? Let's take a look at that. Whoops, I went too far. So Japan, unlike Iceland and Hawaii, is at a subduction zone, which means we're getting recycled magma. We're getting rock that's being pushed under. This oceanic rock is being pushed under. It's being melted down, which means that this rock is going to have a higher silica concentration. There's more silica in this magma. More silica, as we know, means more viscosity, thicker magma. It's also going to be a little bit cooler magma than what the type you'd get from deep below the mantle at a divergent boundary or hotspot. This magma is a little bit cooler, and cooler also means thicker, stickier magma coming out of this volcano. And because it's at a subduction zone, there's a lot of subduction going on. We've got the Pacific plate subducting, the North American plate is involved, the Philippine plate. All of these plates are kind of subducting underneath the Eurasian plate. Japan ends up having a lot of volcanoes like this. We've got over 100 volcanoes in Japan. A lot of them tend to have this very thick, sticky magma because of the subduction that's happening there. Right? So Japan was really built by these volcanoes. It's our classic island arc. So those two kinds of eruptions that we just saw, they do have names for them. And so as the magma rises, you either get an effusive eruption or an explosive eruption. And this really depends on the magma. It depends on the gas content, it depends on how thick and viscous it is, it depends on the temperature and how much silica is inside of that magma. So if you have very low silica, low viscosity, and you have a very easy flow, you're going to get a quiet or effusive eruption, is what we call it. If you have high silica, high viscosity, slow flowing lava, you're going to get the vent plugging up much easier because that lava is not able to flow away, kind of just stays in the hole of the volcano. Plugs it up, pressure is going to build, and that's when you get explosions. So go ahead and add these two. These are two vocab words. Add those to your vocabulary list. Effusive eruption and explosive eruption. Pause right now if you need to do that. So here's just an example. We've talked about pahoehoe, we've talked about ah. Those are both examples of quiet eruptions. The ah is a little bit more viscous than the pahoehoe. As you can see, it's kind of chunkier, it's a rougher surface. But they're both still pretty low viscosity, and you get very quiet eruptions, like the ones in Hawaii. An explosive eruption, as we said, has higher gas content, higher viscosity, higher silica, and the magma is really going to plug up and cause pressure to build. And when that happens, that we call that a pyroclastic flow. This is a type of explosive eruption, and it hurls ash and cinder and bombs, which are just large pieces of rock and magma, into the air. This is very dangerous. So this is also a vocab word, pyroclastic flow. Go ahead and add that definition to your notebook now. Pause the video to do that. You're also going to want to create this table in your notebook. So you're going to want to pause the video now so that you can create this table on your next available page in your notebook. All right, in this next segment, we're going to come back for part 2. We're going to be looking at how they classify different volcanoes, and they do it in 2 different ways. They classify them as either active, dormant, or extinct, and they also classify them by the shape. And the shape is really determined by the type of magma that is coming out of the volcano. So in part 2, we're going to look at those, and we're going to wrap up. Right? This has been great, guys. I will see you tomorrow. Have a nice night.